let's look at one last theorem. It's called the divergence theorem. So first off, what we're going to do is look at, there's not the most usual version of Green's theorem, but if C is the boundary of D, then the integral over a closed curve C, so that's what that little circle means, you can just almost ignore that circle, of p dy minus q dx. Now again, this is not the most usual version of Green's theorem. This ends up being the double integral over the two-dimensional region D of the partial derivative of p with respect to x plus the partial derivative of q with respect to y dA. Okay, so from one version of Green's theorem we can get this other version of Green's theorem, and if F happens to be a two-dimensional vector field with components capital P and capital Q, then actually the integral that we have right above here, it can just be rewritten as line integral over the curve C. Let's draw that C a little bit larger there, of the vector field dotted with n d lowercase s here. I know this looks a lot like the flux integrals that we've seen, but it's just a lowercase because this is all just in two dimensions, okay, of the double integral over d, and then you might recognize this, at least it's a two-dimensional version of divergence. So divergence of the vector field f dA. Now, if you don't recognize this too much quite like that, but you might recognize the derivative of p with respect to x plus derivative of q with respect to y plus derivative of, let's say, r with respect to z. Okay, but this is a two-dimensional version. And this thingy here, just to comment on it, this is really the flux of a two-dimensional vector field f equaling components p and q across a closed curve C. Now, if you're not sure if that's all working, no big deal really. You can just think of this theorem we're about to introduce, the divergence theorem, as if it's its own separate thing. But really, it's meant to be a generalization of this thing that was just presented, and it's a little obscure, right? So I get if this is like, well, where did this come from? And we haven't really focused on it. But this new theorem we're about to introduce is really just a three-dimensional generalization. Okay, so if you want, just think of this as its own separate theorem. We'll try to connect all the pieces a little later. This theorem is actually really nice. After looking at Stokes' theorem recently and surface integrals and flux before that and all that, we've looked at some very challenging things. You're going to find that this is a very nice last topic to have. So if you have a three-dimensional vector field, whose components are going to be called capital P, capital Q, capital R for now, and capital S, oriented outwards, is a closed surface and is the boundary of the solid region. Solid, trying to get at that this is a three-dimensional thing. Okay, solid region capital E. Then the double integral over the surface S of f dot n d capital S is equal to the triple integral over E of the divergence of the vector field f d capital V. Let's just, okay, so again, the divergence theorem, here it is. We're going to make a couple comments, of course, right? But this is just meant to be a generalization of this thingy here. If you don't see it, don't worry about it too much. Let's just make some comments so that we can start connecting things like the flux that was there. This part right there, yeah, this is also written. The book author seems to really enjoy writing it as double integral over the surface S of vector field F dot D bolded S, so we'll write an S with an arrow, I think it's actually more helpful to write it with f dot n. But then let's also comment what this integral here really is. Yeah, this is the flux. The flux of your vector field f equals p comma q comma r. Those are the components across the closed surface, capital S. And the point is that that's going to turn into, if we like, into a triple integral instead. And this is going to be really nice. So let's make a couple other comments here real quick, since S is the boundary of E. It's in the language here, right? S is the boundary of the solid region E. We can also write that this left side, this side here, we can write this as the double integral over, instead of writing the S that's right there, we could write just boundary of E. Okay, that doesn't really actually change anything. Of f dot n ds. Or we can also write this as double integral over boundary of the three-dimensional region of f dot bolded s. So we actually have 1, 2, 3, 4 ways of writing the same thing. It's just, do you want to write S or do you want to write boundary of E? Okay, and by boundary of E, let's just try to clarify, like in the past we were talking about a surface itself, S, and its boundary. If a surface was made out of paper, the boundary was where you could possibly get a paper cut. Now E itself is a three-dimensional object, right? Think about like take some Play-Doh and ball it up, right? So that's E. Then what's the boundary? It's the portion of the solid thing E, which is, let's say, exposed to air. So if we think about maybe capital E being like a shot put, yeah, then the surface is, well, yeah, the part exposed to air. Maybe let's try a little better. Let's say that you talk about an orange. If capital E is all of an orange, and I mean like the part that you eat as well as the peel, then the boundary would be the very, very, very tiny outside-most layer of the peel. Maybe it's even better with an apple, actually, because the peel is thinner, yeah? So if E were the apple skin and everything inside the apple, then the boundary, yeah, let's write that. So if E is an apple itself, including the skin and so on, then the boundary of E is the skin of the apple.